Yeah, see it now. Yeah.
Okay. So, I'll kind of back myself into each of these, but I think Steve, for example, you had made a submission where it was like, I think in the 70s or something. Um, and the best ones we know are 0.98 and stuff, but we'll ignore that. We'll kind of figure our way to getting there and see how far we get to. So these are three different libraries. The first one, as the name says, and we'll spend some time just looking at each of these. The first one used Torch Audio, and that, as you can see, again, these are all very basic. There's nothing much in them, as you'll see in a minute, but it seems to give some pretty decent score using Torch Audio. So this is the audio library in PyTorch. And Gautam, you had asked the question, hey, can we do that with PyTorch? I've seen several notebooks which use PyTorch to do the analysis. So the answer is yes. Then the next one I tried, and we'll see why it's so terrible, but there's a fast audio library that works with FastAI. And by the way, these both use the FastAI library, and that made it incredibly simple, as I'll show to you in a minute. It's kind of brings out the best of the FastAI library and how quickly you can set things up to get to where you want to go.
Are either of those in FastAI, or is just you're using FastAI to use the other libraries? So is Fast Audio
they are in
part
FastAI.
of right? And the Torch Audio is in FastAI as well, is it?
Yes, the Fast Audio is in FastAI as well. Yes, because it basically, since FastAI is built on PyTorch, you can just use Fast Audio from PyTorch, but the infrastructure is FastAI.
Okay.
We'll look at each of these notebooks in turn. But yes, short answer, yes. And then there's a Librosa library, which I think you'll see a lot of when you're processing sound. And in this case, the person uses basic, it doesn't use FastAI. He uses basic PyTorch. And as you can see, that necessitates a set of functions that FastAI abstracts. And again, you can see that one gave a good result as well. And I think I know the answer, or at least, I kind of ignored some warnings when I was using Fast Audio, and the result is the low score. So if I go back and fix it, I think that should address it. So this is kind of in the range. And as I mentioned, I think the best scores are in the 0.98. So you can see that there's tremendous progress to be made. And at least I have a bunch of ideas, and maybe you can think of many more as we go through that and see all the ways that we can improve things to get from here to some higher scores. With that said, let's go through each of these in turn. So I'll go through the Torch Audio notebook first. So I'm just kind of going to, this is simple. It's copied, as I said, but I'll just go through the fundamental way or manner in which they go about it. This one is, as I mentioned, fast AI based, but uses PyTorch audio and Torch Audio. And let's see what he does. And I was kind of very impressed with the simplicity of what is done here, but it still, as you saw, gets a fairly decent score. So basically, you import the vision node modules from PyTorch, and you'll see in a minute why that's needed, and then import Torch Audio. Set the paths to be the basic path, and then the training and the train TP, which are the two positives. So one of the things you notice right off the bat is, this notebook doesn't use the false positive. So that's an open question of how can we combine the false positive and get the result to be better, because that's provided, and obviously there's some useful information there. So that's just a potential future improvement. And then you get the FLAC files, and you'll see from the link I posted earlier that the FLAC files are just a format for storing audio files, which provide amplitude versus time. And this is the amazing thing about FastAI and also the PyTorch Torch Audio library. I haven't played, by the way, with each of these libraries because I just wanted to get the framework working first, and then I spent some time looking at the various ways in which I could improve the things I'm doing. But so you can set up some transforms. The first transform is just creating a MEL spectrogram with the number of MELs to 32. This is where having a good understanding of what the hell number of MELs is and what a MEL spectrogram is from the link to the lectures I posted earlier is useful. And this in the 30-second soundbite there is a spectrogram helps you convert, get frequency plot, combination of frequency and time. So the traditional audio plot is just, the FLAC files are just amplitude versus time. There's no indication of frequency, and you can use the short-term Fourier transform to generate a set of frequencies versus time and the amplitude plotted in color on that graph. So that's what a spectrogram is, and the fact that our ears are more sensitive to lower frequency bands. Sensitivity is not the same as frequency goes up, and that's the reason that MEL spectrograms are used. And the NMEL shows how many frequency groups of MEL spectrograms are being used in your plot. And you make the frequency, in this case, you convert the amplitude to dB, which basically makes it a log plot. Okay, and this is where the fanciness of FastAI comes into play, because all you do then is create data blocks, which you use a transform block to, and apply these transforms to the input FLAC files. And because all you want is multi-category, because there are 25 species. So saying that it's multi-category automatically in FastAI gets you the relevant laws and sets you up to do multi-category classification. And then it's just a matter of loading get X, which is your input, FLAC files, get Y, and this is again a kind of a fancy way, but bottom line, what he's doing is, if you go back and look at the training files, which are in the traintp.csv, you'll see that you take the stem of that file and then you take the species and you make a set, because there are cases, at least I saw of one instance, there may be multiple instances of where there are recurrences of a species in a single audio file. So by making a set, you make that a single instance of that, because all you want to do is detect whether that species is present. So you don't really care if multiple labels of that species are there in a recording, as long as you can recognize that that species ID is there in a recording. And then in this case, he overloads it. He just creates the data loaders also, but you could separate that. So the beauty of FastAI is in just how quickly you go from creating the spectrograms, which is using, in this case, Torch Audio, and then boom, just create data blocks and create the multi-category block. The loss and everything else is automatically created because of the data block data structure. And then you define a learner, use the data loaders. In this case, he's just using ResNet 18 is the reason to have the vision import, because that's where you have the ResNet 18 that you download from. Actually, this gives a warning, as you can see here. Nowadays, I think you can do n equals 1 directly instead of a config. And then this is another place where, again, I can change in order to get better results, or at least be able to see how well this particular notebook is doing against the metric we care about. Here, the metric specified is just multi-label accuracy. This is not the metric that the competition uses. The competition obviously is, the LWL wrap, label weighted, label rating, average precision. And again, this is another opportunity for improvement. By the way, one other opportunity for improvement here is we've just done this transforms just create the MEL spectrogram. We haven't done, once the spectrogram is generated, we could also do augmentations on the image itself, which I'll show being done in one of the other notebooks. So you can throw a bunch of augmentations as well. And the other, so that's yet another improvement. And then here he directly does fine tune. This is again something where you could potentially train for a number of epochs, freeze, then fine tune, and then predict. But those are all potential improvements to this notebook, and you can see that already we are getting pretty good results. Well, good in a relative sense, I guess, but 62% accuracy. So you train that, and one of the things that I thought was interesting was this runs all on the CPU. So I guess we didn't, and I have to look into that. The learner, I would think, would have moved the model to the GPU, but I didn't see the GPU, even though I had it on. By the way, I turned it on, but it ran on the CPU, which is the reason that you can see this thing took a heck of a long time. It took more than an hour for me to run. The times are in the 13 minutes per epoch. And I think the next one I used the GPU, and it was only about 2 minutes. Once that's all done, then it's just a matter of running inference. So for inference, you obviously use the test files, use the data loaders, and do the predictions, and then submission. That's it. So in this case, again, another thing you notice here is this notebook completely doesn't use anything with respect to fmin or fmax, which is provided to us for each of the FLAC files. Doesn't use tmin, tmax, which are provided for each of the FLAC files. What else? Also uses ResNet 18. Maybe we could use ResNet 3450, ResNext, EfficientNet, various different models. You saw that the NMELS is 32. We could, if you again refer to the lecture, we could go even up to, there's no technical limit, I guess, but even 64, 128 number of MELS is something to try. And as I mentioned, various augmentations. So those are all things that you could try with this notebook, and obviously get the model on the GPU as well to reduce the training time. But that's kind of a basic FastAI stuff. It seems to work pretty good. Any questions or thoughts, comments?
Sorry, what was the score you got from this one? Was this the 68 score or the 0.28 score?
The 0.62.
All right, so yeah, that's pretty good, yeah, for how simple it is.
Yeah, I thought that, for the simplicity of it and just throwing it in, a few lines of code, it's pretty good.
Yeah.
The ResNet has untrained weights, right? Initially. Because the images are different from what it's trained on, the normal ResNet. Or does it use the same weights?
Do you not get the
weights that it got from ImageNet as a starting point? That's why after that you fine tune. But that's where you were saying you could train it on these for several epochs.
Nature of images are completely different, right? So it's better to start with untrained weights than.
Yeah, you could start, but yes, but I would expect it to be less performing. That would be my guess, Gautam. The reason being that for the lower level layers, it's pretty, what it learns is still relevant to these images. It's only when you get to the higher layers, which is probably a reason that I would guess. Again, these are all guesses, but it would be worth trying with actual experiments. Is I would guess that if you went from 18 to 50 or 100 or something, you'd probably get worse, because what I recall from the prior discussions is many of the higher layers, meaning the layers closest to output, train for relevance to the labels, whereas it's like much of the lower layers train to relevance of the basic composition of images, like vertical lines, horizontal lines, blah blah blah, circles, things like that. So if you had a very deep network, then you're wasting a lot of resources training for things that you eventually are not using, or at least by using the ImageNet weights, those weights are not relevant. But with 18, much of the lower layers will be relevant. So and the other fact is we only have, I forget now what the number is, somebody can look in EDA and say, but we don't have as many images here as, for example, with ImageNet and stuff. So from that perspective as well, it may be better to start off with the ImageNet weights, but worth trying both ways to see what results.
I thought I saw in another example that there is a pre-trained ResNet for audio. I don't know if it was used here, but like some.
But yeah, I don't know about audio. So you're saying a ResNet just trained with a lot of audio spectrogram images?
Yeah, I think I saw it in another notebook, but I can check.
Interesting. The one thing I can say is there, in fact, when we get to the third notebook I ran, that one uses ResNest 50, and it uses existing or pre-trained weights. Now, what he trained it on, I don't know because he doesn't say, but that uses existing dictionary weights. I'll get to that. Okay, any other questions regarding this fast AI torch audio? And of course, I haven't played around with torch audio. Sorry, no, this too.
Okay. Because I thought data block was removed, or
no,
that was
data block
bunch.
is very much too. Yeah, data bunch was removed. Yeah, you're right.
So yeah, like in the line there it says fine tune. That wasn't in FastAI version 1, sure it wasn't. Is that equivalent to
that's right,
freeze or whatever? Is it?
Yeah. Yeah, this is 2.
Right.
Okay, next, the one that was miserable score. Here, I think that's my fault, not the fault of the libraries or the code, but by the way, interestingly, the guy never submitted the notebook that he created. So I think that was part of the reason. He probably saw that the scores didn't. Again, it's more of a starter kit. And again, this is one where I went back and forth and had to make some changes. He kind of does things which we don't need to do. So I simplified it just by trial and error. So anyway, I'll post the notebooks as I said. But again, very simple, and we don't need all this stuff that he does. In this case, it's fast audio. So there we use torch audio. Here we use fast audio. And again, the path thing, create the train and the test, load it, listen to it. This is the basic waveform that you get from the FLAC. So this is amplitude against time. And you can even listen to the sounds. Sometimes very interesting, but sometimes it's just a lot of quiet noise. This one has a lot of activity. And let's say, basically, again, create this train stuff, drop everything except these two things. The goal of what he's trying to do is, as I mentioned, every recording ID could have multiple species ID. So he's just trying to create that by combining into the same. If there is a single entry for a recording ID, he wants all the species ID comma separated. So that's what he's going through. He makes them a string and then combines the various things. And this, you can see, I wanted to just see a case where this actually pays off, where there's more than one species ID. And you can also see in this case, I don't think he does the set thing, which we saw in the previous notebook. So that's the reason that these 216 show up. Then we build the data loaders. And here's where, for example, we use the fast audio. And there are some configurations you can use in fast audio. Again, as I said, I haven't spent time playing with the libraries or kind of exploring them. And this is where I think things went wrong as to why this notebook gave such poor results. You can see that this NFFT of Y12, when you create and try to do the config basic MEL spectrogram, it complains, right? Or it doesn't complain, but it gives you a warning. And it says the value of NMEL is 128, which is the default, I believe, may be set to high. Now, if you recall in the previous thing with Torch Audio, that was set to 32. So here and these are related quantities, then NFFT is related to the number of MEL spectrogram, I believe. So I need to find a way in playing with the library to specify potentially not NFFT, but NMELs or the combination of NFFT and NMELs so that this particular thing doesn't occur. That's at least my first, it's going to be my first attempt to fix the issue and see whether I get a better score. But the other thing you can see is here, again, this being fast AI, you can do data augmentation really quickly and easily. So data augmentation is adding noise, it's adding white noise, and is doing some signal shifting. Again, I don't yet fully comprehend how these things, what these things specifically do. I mean, I can obviously vaguely understand just from the labels, but that doesn't mean I understand what effect these have and what other augmentations I could be using. So that's something, as I mentioned, to dive into. But then the rest of it, it ought to look very familiar. And the cool thing is you can do the item transforms to do the data augmentation. And these things, which is another cool thing that FastAI does, Jeremy has said this multiple times, is, you know, just like he does in video and stuff, he does the audio to spec as a batch transform. So this runs on the GPU, which is cool because you can parallelize a heck of a lot of the FLAC files getting converted to MEL spectrogram. So the spectrogram generation itself, because you run it as a batch transform. So if you're running, you know, batches of, I forget what, 24? Yeah, batch size is 24. So 24 of these FLAC files get converted to the audio spectrograms in parallel, or at least using the GPU versus using the CPU when you're doing it, or at least when it was done in the previous notebook again. So you could potentially, I think, do that in the other notebook as a batch transform as well, because it uses FastAI. But I thought that was cool. The two kind of different things this notebook does is, one, it shows, hey, I can just throw in augmentation. Second, I can throw in batch transforms to get my spectrograms. The rest of it is very identical to the other guy, but because, and this is my guess, of this poor conversion to spectrograms, you know, for example, it says the NMELs thing may be set too high. You see, I mean, I did plot these and these look. There's the other thing is, you know, you could plot this in the other notebook as well, but here is plotted it to show what each of these look like. The other thing which hasn't been done here, if I'm not mistaken, although I'd have to go look at the basic MEL spectrogram code of what audio to spec does in the fast audio to figure out whether the amplitudes have been converted to log as well. Right, because you can see, and you can see some of these, they don't show a good frequency spectrogram things where it's all in the higher frequency spectrums. And then you just do the learner again, as I mentioned, instead of a config, you can just say n is 1, do the LR find, and then fine tune. Here I ran, and as I mentioned to you before, this time it ran on the CPU, so you could run each epoch just for about 2.5 minutes or so. And then create the submission file, predict, submit. Again, fairly, this where the power of fast AI and the fact that you're creating the multi-category block, data loaders, blah, 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 training, all this kind of infrastructure that's built in really helps.
What was your table down the bottom? Sorry. The one that's all set to 0.5
file for.
Yeah, that one. Why is that all 0.5?
This is basic submission sample. That's just a sample.
Oh, right. Sorry. I thought that was your results.
Yeah, no. Here, that's
right. Okay.
Okay, so we saw 2 examples of fast AI, one using Torch Audio, the other one using fast audio. Again, we can play with each of these libraries, Torch Audio and fast audio, and get familiar and kind of see what are all the capabilities that it provides, and then use that. And as I mentioned, all the things I mentioned previously, this one doesn't use tmin, tmax, fmin, fmax. It does some augmentation, so I guess that's somewhat addressed. Although, as I mentioned, understanding what augmentations to apply, which are the ones that give you the best results. And obviously, I've screwed up the NMELs or NFFT numbers in order to get these poor results. So that needs to be improved. This one uses ResNet 18. Again, anything there that can be done and different networks. Those are all the thoughts. And by the way, if there are other things you can think of that can be done, again, Gautam's point, you may want to train, and if you use point, if you find weights or these networks with weights trained on spectrograms itself and a ton of them, then that would be even better. Things like that would be another source of improvement potentially. So all those things can be done once you have this basic framework set up. Okay, so that's example 2. And then let's see, let's go to example 3. Okay, here I'm using the Librosa library, which is again a dedicated sound processing. Instead of Torch Audio or fast audio, this is, and now I'm not using fast AI anymore. I believe, yeah, this is still PyTorch based and uses Librosa library for at least the sound processing. Okay, so use import Librosa. Librosa gives you the samples and the sample rate when you load an audio file. So, and the samples gives you how many, this is just numerically the quantity of samples. And this is the default sample rate for Librosa. So when you don't, you could specify a sample rate, if I recall, when you load a file, so you can tell it to sample, as we'll see in a minute. But in this case, because you don't tell it what to sample it, or the rate at which to sample this audio file, which is a FLAC file, it gives you the default rate and the number of samples. So it gives you the default rate and the number of samples. And keep in mind that you can actually detect the duration of the sample by once you have the number of samples and the sample rate. So those three quantities are interrelated. So if you know two of them, you can compute the third. So if you know duration and sample rate, you can calculate the number of samples. If you know number of samples and sample rate, you can calculate duration. In this case, for example, you can see he says, wait, I can do this at a different sample rate. And then it's the same thing, play that, display that. And then here is something which is a little more, here you can display the spectrogram. We could have, but those two notebooks didn't display the spectrogram. I mean, you can go and add in the code to display it. No big deal, but here he displays it. And this is where, again, you can see the fact that, this is now in the frequency, but most of it, as you see, most of the amplitude is right here, because that's where the lighter colors are, which shows that the amplitude, the high amplitude stuff is right there at the lower frequency ranges. So what you do, therefore, is make the y-axis log. So this is what, for example, in the prior notebook, you saw this amplitude to dB and basically to decibels, and that converts it to log. So that's essentially what is being done here, the amplitude to dB. So then you can see that you see the lighter colors much here, and you see this thing at that high, the same frequency you saw here. Right, you see this at the same range of frequency. There's a whole bunch that this notebook has, which until and unless I find the reason to do this, and this might be another source of a bunch of improvements that we could potentially do. There are a whole lot of other parameters like spectral centroid, spectral roll-off, spectral bandwidth, the number of zero crossings of the sound signal, and then something called Mel frequency cepstral coefficients, and then chroma feature. But I mean, while the notebook generates a bunch of this and shares the pictures, I want to kind of figure out whether these things are going to be relevant in helping get a better score, and then spend time understanding and or applying them. At least for now, I don't care. So you can look at the notebook, reference notebook, and learn the code to do all this stuff, but I didn't bother. And then he's just using the inference from another notebook. This is again, as I said, Torch data loader, basic Torch data loader, and uses ResNest 50 as the pre-trained network. And then number of classes. This was something which I found strange. He's using a sample rate of 16,000. And I was somewhat puzzled as to why that's not higher, and whether higher would give us more of a benefit. The duration is obviously the duration of the sample, that's 60 seconds or a minute, just the paths. And now you start defining the classes. Remember that in this case, we use Librosa, but he's using a class to compute the Mel spectrogram for each FLAC file. Okay, so the call basically generates, in Librosa, you use Librosa feature Mel spectrogram. You give it whatever the input is, and then the sampling rate, the number of Mels, min and max frequency. And then again, amplitude is converted to dB, which means you make the amplitude the log, as we saw earlier in the picture, why that's desirable, and then return the Mel spec. So this is just a code to compute the Mel spec. Then this is just, remember that ResNest and even Res, all these basic ResNest next models use 3 channels. whereas our input is a mono single channel in the spectrogram. The way we got around that, and again, one of the simplicities of FastAI, you just say n in is 1 and you're done. But you don't have that here, so we need to convert the mono to a color channel and then normalize, standardize, do all that kind of stuff. By the way, interestingly, I mean, this just occurs to me right now. I don't know whether standardizing and minimizing would be helpful in doing, in processing even if you use FastAI and just give it a single channel. Just something worth trying as well. In this case, so he just stacks the X, makes it a 3-channel. It's the same input, stacked as 3 channels. And then standardization is the mean and standard. Normalization is, just normalize it between 0 and 225 and then return the values. This normalization of an image is then dividing it by 225, get it in that range, and then use the mean and the standard deviation. Here, and I haven't yet, this is another thing that I vaguely know that is done, but I haven't dived into the details of cropping. I mean, what he's doing here, the code is simple, but when you would use it, crop or pad, and this would be relevant if you're cropping the input sound and taking pieces of it and creating a spectrogram and analyzing it. Remember that so far we haven't done that. In the first 2 notebooks we saw, and even in this notebook, at least in the initial, we'll just take the full 1 minute and then just create a spectrogram and throw it into the model and compare it or predict on the test set. But if you were to crop the input sound, that's again a question of when would you do it, how would you do it smartly. Don't know the answer at this point, but something worth exploring further. But so this one just says, how you go about cropping or padding, and when you pad, you just pad with zeros. So you can see that that's what is being done when the length of Y is less than the desired length that you provide as part of your input. And you obviously do that if it is train, and otherwise just pick a random number and go up to length if it's test. Then this is creating a data set for the specific data that we have in the competition. And here is where, again, you can see that the default value specifies it's 128. Obviously, number of classes is 24, and fmin, fmax. And you go about doing the various things to get the appropriate waveform converted. Some helpful, what is the length of the data. This part of the code, to be honest, I haven't dived into. I was working on it late last night. But I believe this is where you can crop or pad depending on what you supply as input, and then of course just getting the get item for getting the particular values at the index, and then you just create the mel spec, convert it to color, normalize it, and then return it. That's all the get item does. And then the duration, as I said, is just the fact that you can get the duration. So from Librosa, you can get the duration of the flat file, with the duration being the amount in time. Let's see. Then you just do some data processing and get basic setup, and then you get to inference. And here it runs larger batch size with multiple number of workers. So in parallel, sample rate here is this 16,000. And you load the test data with a batch size of 40 and number of workers 2. This is where he's loading the ResNest 50 model and the actual state dict directly from the pre-trained weights. And where this comes from is you can create inputs in your notebook. And as you see here, I have the second set of input besides the data input. And this is where he has the checkpoints of the training he has done with ResNest 50. Yuri, was this something you were referring to or something different?
Actually, so I was wrong. It was ResNet. And actually, we went through the same notebook last time, but we didn't go into details. So we only kind of looked at the first part and looked at how data looked. So yes, that's the notebook I took and I copied it and ran. Because it looked simple
at
enough.
Least for inference, what he is doing here is just using pre-trained. But that's where I was, I'm not sure what he has actually trained it on because he doesn't say. And right, it's just that these are trained weights at various points that he loads, and then evaluates. This is the ResNest versus ResNet. Again, I don't recall the difference. I'd like to go and check that. Does somebody know the difference, ResNest to just the traditional ResNet? Something worth checking or following up on, just so we know. And then he just does the predict, and you can see, obviously the code is more involved because a lot of what FastAI does, you have to actually go in and do it. So, for inference, you have to actually go in and run the prediction code with X's and Y's, and predicts, and then create the submission file, and that's it. And this one, I think, gave me intermediate results, not as good as the very first Torch audio based thing, but pretty close, 0.589 versus 627. And as I said, I still have to understand, at least in this basic notebook, if you see, he doesn't seem, while some of the infrastructure is set up, I don't think he's using any cropping or anything of that kind. He just throws in the full thing. So he has a bunch of stuff he has built in, but he's not using that yet. So this whole cropping thing is something that I'm interested in, but I wanted to just get some basic things done before I move to the questions of, okay, why would you crop and how does cropping help you get better results, and how do you go about smartly cropping? Because you don't a priori know which portions of your input signal have relevant species information versus not. So do you crop randomly, or do you crop at fixed intervals, and do you overlap the crops, or what do you do? Obviously, cropping would be interesting because I guess you get smaller time intervals, which means you get better accuracy, because you're not looking at an image which is, corresponding to 60 seconds of time. You could potentially do it at 10 seconds interval, in which case you would have 6 crops. This reminds me of what was done with Sevestal, which was one of the competitions we had done earlier. Any comments or thoughts on this one? So I just wanted to get some, basic capabilities up and running, and then worry next about how to improve and what are all the things that could be done. And then obviously this whole cropping padding thing is something that is worth exploring, of how would you do it, and what's the smart way of going about it, and why would you do it.
How did you choose these 3 notebooks? Did you choose them because they were fast AI for the first 2?
No, I didn't. I mean, obviously we don't want to choose anything which is good in the beginning. I chose them just because I felt they were basic and simple, which is what I wanted to get. I wanted to understand pretty much anything that the notebooks were doing, and start at the foundational level and then go up. And them not just being EDA, because I think I kind of understood over the last couple of weeks what the EDA did. And again, this notebook has a bunch of EDA that I cut out because, as I mentioned here, I want to understand the relevance of any of the other things that are, oh, by the way, the other thing to mention, besides, I cut out 2 things. One is this whole thing around spectral, and he has pretty pictures and all of these features, but I wanted to understand whether I would end up needing any of these features in what we were doing to get the better score before I spent a lot of time on those, understanding or generating them. Secondly, what I did cut out here is he ensembles this model with a bunch of other models in the notebook. I cut that out because I wanted to kind of be, again, as I said, wanted to understand basically what this process, if you will, does. When I say basic, keep it simple and just get me the results, rather than begin to ensemble this model with potentially other models that I think he ensembles with some pre-existing results of some XGB oriented model, which again, I didn't want yet. I just wanted, Steve, the other reason I chose was this thing gave me 3 different libraries, like Librosa, Fast Audio, and Torch Audio. And the next one I wanted to go to, I ran out of time, is a TensorFlow basic one.
Right.
So if you can, Steve, have you posted the link to the notebook that you used?
I'm not sure. I just found one, a basic one or
whatever.
whatever.
The TensorFlow one, I thought, right? So if you could post that, that'd be interesting to look at. So I think those were my reasons. It gave me 3 libraries and very basic, so I can start from the ground up and see how all I can go about improving things and understand the concepts. That is what drove me to select these notebooks. And as you can see, I mean, they are fairly simple, straightforward notebooks, which is probably the reason they get 4 results, but that's okay. I want to then think about how to go about improving it, or at least even if later on run out of ideas, but when we see ideas elsewhere, I can kind of see what problems they address.
I linked weights and biases report where a guy in the chat where a guy compares a bunch of hyperparameters for, I think, generating this spectrograms, and he has like an extensive comparison, and he does it on that ESC50 dataset, which is, I think, like popular benchmark. And
is this by any chance the one you're talking about?
Oh yeah, yeah.
Yeah, I haven't read it, but I had bookmarked it.
Yeah, I haven't read it yet too, but it looks like he has like I think it can be used like a good starting point for the hyperparameters for the like this spectrogram generation.
Yep. So this was one I caught because this is referred to, by the way, again, I'll post these links. There's an example tutorial on sound classification using fast audio. What's this? This is a fast audio usage example by this Zach Mueller guy. And this is the GitHub location for fast audio. But to your point, Tato, yeah, this is something that I was going to look at in more detail of if you're using ResNet 18, what are all the parameters and how do you best choose them? And you can see some of the things here, hop length, which I've talked about, I think, last week, which is, when you do the STFT, which is a short-term Fourier transform, how much do you overlap the windows that you choose? Yeah, and then the window length, which is the set to FTFT size. So this is where the NFFT thing I set, I think, in the second notebook of 512, which was causing me problems. So this will give me, reading this will give me a better understanding of what to set that value at. NMELs, we saw there were a couple of different things. Shows 32, I mean, in this case, he says 32 is definitely too few, and he says 128, but then 128, as you saw, with NFFT of 512, gave me problems. So that's something else. Looking at this, I'll be able to better understand. This is the NFFT. So that's the parameter that he talks about, see how much to set it at.
Yeah, one thing I'm wondering about, if this does this transfer, if you say choose good hyperparameters for this spectrogram creation using this ResNet 18, and then you can just like plug in much bigger ConvNet or whatever you would like to use, and yeah, so I'm curious if it would it be that the same set of hyperparameters probably makes most sense, or maybe for like really larger models you might like get better results with slightly different hyperparameters. So maybe like because of like capacity, a larger model can use some finer details or something like that.
Yeah, and I think that kind of an experiment or something I would be able to do now, because I could, the first two notebooks use ResNet 18, right? So I can just throw ResNet 18, and the second one that I have uses ResNest 50. You could again use, instead of ResNet 18 in the first couple of ones, or either one of them, throw in ResNet 130. I think that is the 134, if I'm not mistaken. There's something in the 100, 150 or 134. There's a huge one. I think FastAI has the pre-trained weights for that too, but if I recall correctly. But yeah, to your point, the question is, would these parameters hold steady as you varied the size of the convolutional network, right?
I think you might have some comparison towards the end as he tries DenseNet 1-to-1 or something like some bigger
architecture.
So yeah, I
152.
also haven't figured read this report in details, but I guess it might contain this information as how do you need to change your maybe spectrogram generation process as you scale up.
Yeah. And it says DenseNet does better, so that's another interesting data point. And then that's what I was mentioning, right? One of the things is, are there, and this is all ResNet, so there is ResNest, and then there is efficient nets as well. So yeah, quite a bit of, and this one definitely seemed very,
also, you see there are like some strange patterns here as you lose accuracy when you move from ResNet 34 to ResNet 50 and to ResNet 101.
yeah, it's kind of interesting, but this whole blog post I thought was very fascinating. Yep. So thanks for highlighting that. I think worth spending time looking at it and understanding and or trying different things out that he has tried as well. Trading 1,430 models. Okay. Any other inputs, comments, thoughts?
Sorry, Yuri just posted the question there about submitting from a notebook into the chat. I wasn't sure exactly what you mean, Yuri.
I think I ran into that before. Is it still like after competition is over, should they still be able to run notebook, save it, and then like click on the output and submit the file right from the GUI? Or do I need to save? Okay.
Yeah, sorry, can you see my screen?
Yeah.
Yeah, so I think I've got like a notebook around here somewhere. Yeah, so like this is the notebook I ran in the competition. So yeah, like I just copied it from this person's one, and then so I get an output which has got the submission file. Yeah, so I think if you just click on that, like I thought, so you just go there to submit, and that's
so so that's what I've seen that before, but I never get to that screen.
Here's why, Yuri, and I was going to ask Steve this too, but here's what I had to do. So when you do it interactively, it seems like that file isn't saved. So what you need to do after you have run the notebook interactively is you see typically you get that thing up on the top which says save, and you click that and you say save and run new. And you can then, as Steve mentioned in a previous conversation, you can shut off your interactive thing then, because if you don't do that, you're incurring double the charges. So once you do save, and then it'll ask you, do you want to rerun the notebook from the top, and you must pick that preference. Then it creates the output file which is saved, and then you can go in and submit that. If you do it only interactively, then you do not see that output file saved.
Yeah, so here in this notebook, I'm editing this now.
Right.
So yeah, like if I was just to run all here, it'll not generate me any output file. Whereas like as Srinivas says, I need to go to save version here, and then you need to do the save all, the commit one, as opposed to don't do quick save because it'll not generate the file. But if you choose this and like choose save on that, like you can see up here now it started to save, and so like now my GPU will be being used twice. It's being used by the editing notebook, and it's being used by the one that's being saved. So I can turn off this one, and like I can leave this now, so I can come out of that, And yeah. So like after a while, when that, you can see it's version 1 still, it hasn't done it, but like when it reaches version 2 of 2, I'll get like an output submission file. This is a submission from the first one, and then I can submit that.
Okay.
So yeah, after you've finished editing, you just need to make sure that you commit the notebook to get the output file, which you can then submit.
Cool, thank you. Yeah, I knew there's like something that I'm missing, but I didn't see what it was. Thanks.
Yeah, it's annoying, and they don't have good documentation which tells you that's what you need to do, which is pretty frustrating. But after you've struggled with it a few times, you don't forget. Okay, if nothing else, again, encourage everybody to try their hand. It's at least easy enough to get it up and running and working. And then, of course, a lot more work to do to get from wherever 0.62 or 0.72 to 0.98 or where the top score is. So there's quite a bit of work, but you can get the basic things running and submit it fairly quickly. So I would encourage everybody to just try it, and I'll post the various links, and I think Steve posted his notebook as well. So
yep.
Okay, any other questions? If not, okay, thanks everybody, and see you all next week.
Cheers, thanks. See you next week. Bye.
Thank you.
Bye.
Thank you.
So.
Bye.